Roger Pincombe. I have been a lead full stack software engineer for a long time, but I also used to participate in a lot of hackathons. So I've won over 15 hackathons, and as part of that, it's been kind of exciting to see the way technology has been moving and be able to kind of have a sense for kind of what's in vogue. So one of the things I made was something called allthepeople.net, which was a large-scale social media data mining system that basically you give me an email address or a Twitter handle, I will find everything about people for you online. So it's kind of scary, but part of that used some machine learning to figure out, do these profiles look like the same person? So, as Andy mentioned, this is going to be a very introductory presentation. So this is for people who've heard a lot of hype about machine learning, maybe are curious about exactly what it is and what it isn't, and how you can begin to think about harnessing it for your own projects. So, 1 second here. So what is machine learning? First, I want to dispel some misconceptions. A lot of times in science fiction, you'll see machine learning or AI as kind of a sentient being that can understand everything you're saying and plot against you. You've got the Terminator style AI. So in a technical sense, that is called strong AI. So that's this idea of an artificial consciousness. Maybe in a practical sense, hey Siri, build a website for me, or something along those lines, where it actually understands your intention and it can do things for you the way a human assistant might. We are not there yet. That is not a thing that actually exists. Someday, hopefully, we will get to that point. But it's right now we're still working on baby steps. So whenever someone says AI or machine learning, put away this Terminator style AI concept, and let's talk about what actually does exist. So narrow AI is the technical term for machine learning. So this is artificial intelligence that isn't conscious, but can just do a narrow set of tasks. So this is less on the AI and more on the basically just optimizing math equations. So trained algorithms that can solve very specific tasks. For example, giving it a picture and having it be able to tell you this is a dog, or giving it text and having it be able to translate it between languages. And underneath that is essentially just math. So before I get into exactly how that works and the different types of it, I want to also kind of give you a sense of where you need to be in order to make use of this. So there's a sense of machine learning that is all very complicated. It has a lot of advanced math, and to some extent that's true on part of it. So machine learning right now is at this wonderful point where there is a lot of research being done, and that's the advanced math, that's the PhD, that's the labs going on in Google Brain and the Facebook AI research labs, publishing all these papers about pushing the boundaries of machine learning. But there's also a lot of aspects of machine learning that have been distilled down into simple, kind of easy to use plug and play systems. So the analogy I like to use is when I was in high school, I was a PHP script kiddie, which basically meant I used a language called PHP to make websites. They were interactive, they were programmed websites, but I didn't really understand compiler design or assembly programming or a lot of the lower level stuff that PHP is built on top of. So we're at a point with machine learning right now where you can, without the advanced math knowledge, you can take plug and play systems from things like Keras, which is built on top of TensorFlow, or things like some of the Azure machine learning or Amazon machine learning libraries, and you can take those and implement some of these specific use cases. So for example, Amazon and Azure and Google, they all have libraries where you can give them an image and they'll tell you what's inside the image, or whose face it is, or how old, or the gender of the person in the photo. So those are things that are built on top of some of this advanced machine learning research, but you don't really need to understand what's happening underneath to utilize it. So I'm going to try and give you an overview of the different kinds of machine learning in this talk, so that you can figure out, okay, is there something here that's useful for me, and is there a tool I can go out and use that has it pre-built? If I need to build it from scratch, what's the right terminology so I can talk to someone and figure out, where to get started. So as part of that, let me just run through kind of all the different types of machine learning. Remember, machine learning as a narrow AI solves narrow sets of problems. So there's different algorithms that all kind of fall under this banner of machine learning that solves different types of problems. So the first one we're going to talk about is basic regression. And this is pretty simple. Basic regression is essentially, given some input data and some output data, figure out what the pattern is between the input and output data so that we can figure out the correlation there. So I'm going to start with just to illustrate kind of how silly some of this can be and how it's really not intelligence, but it's just math equation. You know, it's just an equation relating input and output data. I want to show you an example. This is a real world example that actually happened a few years ago. We have this textbook about fly genetics that was sold on Amazon. It had two separate sellers that were selling this book for around $2 million. And the reason they were selling it that high is because both of the sellers had an algorithm that was saying, okay, well, let's look at the average price for this book and sell it slightly above average. And so it turns out they just kept having feedback, building on each other, until eventually they both determined that the price was around $2 million. So even though to some degree this was an automated machine learning algorithm, it really wasn't smart. It's not intelligent. It's just an equation, which in this case is a simple algorithm saying take the average price and add some percent to it, because we're better than the average, so people might be willing to pay more. You can imagine this going the other direction and them accidentally selling the book for free and losing lots of money. So it's important when you're doing anything involving machine learning to look at your data and look at what's actually happening in the real world, track it and make sure it's doing what you expect it to do, because you'll get it's pretty easy to wind up in situations like this where you have completely unexpected behavior because you didn't anticipate some edge case. So let's go and look and see kind of how this works underneath. So as far as, one second here. So I'm going to give you a very simple problem. So this is not deep machine learning. This is just a very simple illustration of how you might use a basic algorithm. So again, this is going to be linear regression. So just saying, okay, well, given inputs, how can we figure out the relationship between the inputs and the outputs? So let's say we are selling ebooks. And we're wondering, at what price could we sell this ebook and have the most sales or have the most total revenue? And since it's an ebook, we could sell it for basically next to nothing and still be making some money from it. So we really want to know what is the optimum price for this. And in order to set the optimum price, we need to have a sense of how many are we going to sell at certain price points. So our inputs are the price and our outputs are the number of purchases. And we want to figure out what is the black box that relates these two. So let's look at some sample data. And again, this is oversimplified, but let's just kind of go along with it and assume that it's real world data for now. So let's say we have some purchases or some prices and purchase counts at those prices. So maybe we've gone through and we've set different prices manually and just trying to see how the market responds. And you'll notice in this chart on the x-axis, our independent variable is price, and then the result is the number of purchases. So, think back to middle school science class, you've got an experiment where you're changing one point of data and seeing how another point responds. So in order to figure out the relationship here, for simple data like this, where they're basically on a line, you do what's called a linear regression, linear meaning it's a line. And we're just going to simply draw a line through the different data points. Now in the real world, it'd be a lot fuzzier. It wouldn't be exactly through all the data points. You try and find a line that kind of best fit all the data. So in this case, we've got a line here that, as the price goes up, the sales volume goes down. So let's say we have a question of, we want to know if we price the book at $30, how many are we likely to sell? So in this case, you simply look at that line you fit, you look at the $30 spot on the horizontal axis here, you go up and figure out where does that intersect the line. So it looks like, around $25, $26, or 26 books we're likely to sell. And yeah, so 26 books if we price it at $30. So again, very simple. We're just relating the data points, finding a general structure, in this case, a line that represents the relationship between the two. Now, this is middle school algebra. I promise this is the most complicated math I'm going to get into. After this, it gets much simpler. I just want to kind of make sure we have kind of an understanding of what things look like under the hood. So you might remember this from middle school algebra, y equals mx plus b. This is the equation for a line. So in this case, y is the number of books we sell at a certain price point. M is the slope of the line. X is the price, so the independent variable, and B is some offset. So if we use an example data point here, 42 equals m times 10 plus b, we can solve for the actual equation of the line. So in this case, negative 0.8 is the slope and 50 is the offset. And you don't need to worry about those specifics exactly, but the point is that equation, y equals negative 0.8 times x plus 50, is basically what our black box algorithm is supposed to figure out. So given the input prices and output sales, all it's doing is figuring out that simple equation. Now, obviously, if we had more complex input, then we would have a more complex black box equation. But it more or less comes down to this: what's an equation that relates the input to the output? So in this example, we have y equals negative 8 times x plus 50. You can imagine with more inputs, it might be a more complicated equation. But the basic equation we have here for linear regression, we can call that kind of the architecture. That is the general shape of the correlation. So in this case, our architecture is a simple line. You also have other more complicated machine learning architectures. So when someone talks about a machine learning architecture or the architecture of the network, think of it as the structure of that black box that connects the inputs to the outputs. And that might be a simple equation, it might be more complicated. We'll get into some other types of architectures later in the talk. But given that simple architecture of the slope of a line, we only really have two numbers that tell us which line it is. So in this graph, you can see the orange line is the line that we just talked about, but the gray lines are other potential lines that might correlate other data. So in this case, it only takes two numbers. So those are basically our parameters of our model. So if you hear someone talking about a model of a machine learning network, that's basically the data that you fit into the architecture to describe the correlation between this particular input and output. So the model for solving, you're looking at pictures of cats versus pictures of dogs might be a different model because it'd be trained on different data. So in this case, we have two parameters, very simple. Now, let's say you had more complex input. You have, let's say you're building a website for people to buy books or buy other items. Maybe there's different variables you could alter, like the size of the buy button, the color of the button, the number of reviews. And so those might correlate to a number of purchases, but it's less clear exactly what the independent variable is there. What's the exact correlation? So, but again, what you would do is you basically plot all of these different data points and the number of purchases, and you'd use a similar technique of finding what is the correlation between the input data and the output data, so that you could effectively have this black box equation that, given inputs of size of pixels and color and all that kind of stuff, would tell you the expected number of purchases. So in the sense of basic regression, also just called supervised learning, you have inputs and you have outputs, and you're trying to find what is the equation between the two that relates the inputs to the outputs. So in this example of selling ebooks, we would answer the question, how many ebooks will we sell at this price point? By the way, I can't hear you guys, so if anyone wants me to stop, or you have any questions, send a message in the chat, and I'll check on that occasionally and try to address any questions. So let's move on to unsupervised learning. So supervised learning is great because you can relate inputs and outputs, but the downside of it, you might have heard that, well, we have a problem with having enough real data or labeling data. You need to have the input and the output to do supervised learning or regression learning. Unsupervised learning is basically a way to say, let's look at the data we have and see, are there any patterns in there that we can exploit without necessarily needing to know the right answer? Let's try and get a feel for the structure of the data. So one of the most common types of unsupervised learning is clustering. So let's say we have a bunch of purchasers and we're trying to figure out, how do we market to them? Maybe there's different segments in our customer group. So we have, our high earners that are not particularly tech savvy. We have our, mid-range learners or earners who are maybe very tech savvy or are in a certain niche or whatever. So let's say, for example, here, and this is a very simple example, so take it with a grain of salt. But our system might have learned to cluster people into, again, this high income group here that may or may not be tech savvy, given they use Internet Explorer. We've got a couple other clusters here as well. And maybe the way we market to these groups is different, or the types of promotions we offer them is different. And so this is customer segmentation. This is something that historically is somewhat manual, but machine learning is great at taking a whole bunch of data that may or may not have obvious correlations and figuring out, oh, hey, there's groups in this data. Unsupervised learning can also be used for other things like, let's say we're trying to figure out structure in the data so that it can be used for other things. So let's say you have just a bunch of text from Wikipedia or from scraping the internet, you can basically run it through something called an autoencoder, which allows you to figure out the underlying structure of how words relate to each other, which can then make other parts of supervised machine learning train faster. And I'll get more into that later in the talk about how we can use transfer learning to kind of optimize our learning speed. But so again, unsupervised learning or clustering can solve the problem of what are our customer or product segments. Figuring out, is there any shape to data that we have? And yeah, to answer a question from the chat, I'll definitely share the slides afterwards. I'll send out a link so you guys can all refer to these later on. So the next type of machine learning architecture that I want to discuss is probably the one most people are familiar with because it's made a lot of headlines in the last 5-6 years, and that's convolutional neural networks. So convolutional networks are interesting because they understand spatial data. So images, anything that's 2D or 3D or where things near each other matter. So for example, given a picture of a dog, it could say, oh, this is a picture of a dog. Given this picture, it could say it's a person. Given this, it is probably pretty confused. These are very important. The work done in convolutional neural networks recently has been really interesting because 10 years ago, computers had no idea what was in an image. You had to label metadata. It was a very time-consuming process to be able to find a picture of something you care about. And now, because you can easily index images based on what's in them. Things like Google Photos is a great example of this. If you ever use Google Photos or Apple Photos on your phone, nowadays you can search for things. You can search for, concert, and it'll show you pictures of things that happened at a concert. Or you can search for dogs. It'll show you all the pictures you've taken of dogs, which is pretty exciting and a major shift in how things work underneath. So how do these work? Actually, so the way these work, at a high level, let's kind of use faces as an example, is they're structured basically in layers of networks that look at things close to each other. So for example, for faces, you're going to have one part of the network say, okay, well, I'm going to look for very simple patterns, like a pixel that's close to another pixel in a way that kind of looks like a horizontal line or a diagonal line. And then you have another layer on top of that that basically says, okay, well, given we have a few of these horizontal lines next to each other, but then we have a few vertical lines in a similar arrangement, maybe that looks like a nose, or it looks like a mouth, or it looks like some part of a face. And then another layer on top will say, well, okay, given these underlying structures, because the eyes and the nose and the mouth are arranged in this relative location, we're pretty sure that that is in fact a face and not a Picasso painting or something. So convolutional neural networks look at things nearby, but they look at them kind of in layers of abstraction. So similar to how you might think of things in layers of abstraction. A lot of convolutional neural network is kind of based on how the brain likely actually interprets things that we look at with our eyes. So it's kind of exciting. A lot of this stuff is kind of based on either directly or indirectly how human brains interpret things. So, it's all well and good to be able to identify pictures of cats or dogs, but what are some other use cases of this in the real world? So there's a really cool company called Cape Analytics I talked with a while back, who is basically using satellite imagery to look at rooftops of houses and determine what type of roof they are and what condition they're in, how large it is. And they actually partner with home insurance companies to be able to proactively figure out, has there been damage under your roof? So let's say you have a vacation home in Florida and you're only living there half the year. You don't even realize that some storm or hurricanes come through and cause damage to your roof, and now your roof has fallen in. So being able to analyze this stuff in mass from satellite imagery and say, hey, this roof looks like it has a problem. We should alert the homeowner or the insurance company that there's an issue there. You can imagine other use cases like this where you wouldn't be able to process mass amounts of images by hand, but by being able to do a first pass with machine learning and then flag things that are worth follow up to humans is kind of where a lot of this convolutional neural networks has a lot of interesting real world use cases. Obviously, with self-driving cars, there's a lot of image recognition in there as well. If you've used any CAPTCHAs recently, so you sign up for a service and it says, hey, prove that you're a human. So, click on pictures of traffic lights or cars. You're basically training Google's neural networks to do convolutional, you're doing convolutional training for their neural networks to help them figure out what is a traffic light, what is a car, and then that data is then used to train the neural networks that they use in their self-driving car project. So another real-world use case for convolutional neural networks or image recognition is, let's say you have a site like Twitter or Pinterest, and there's a propensity for people to upload inappropriate pictures there. So you want to be able to classify images as, are these obscene? Are they not safe for work? So here's an example of a not safe for work image. These guys clearly are not safe to work on this house. So you might have trained a network to identify things that are not safe for work and be able to automatically say, hey, this is not an image that we want to allow on our platform. And depending on how strict your platform is, it might completely ban uploading the image. It might flag it for human review. One second here. I think we got another question in chat. Yeah, so it's obviously this is kind of a contrived example, but if you search online, there's lots of real examples, downloadable neural networks that are just simple, easy to download and run an image through, and it'll tell you how likely it is to contain adult content. So if you're working in an industry where you need to prevent that kind of stuff, you don't have to do custom training on this. It's pretty simple to download pre-trained models that are open source that will handle this for you. So that is convolutional neural networks. In our example of an ebook seller, it might say, is the cover of this book graphically adult? Did some users submit a book, some erotica, and it's a little too risque for our platform. So all these I've talked with so far are taking existing data and either classifying it or telling us how likely things are correlated. The next set is interesting. Given you've trained a network to recognize things, maybe there's a way to make a network actually generate new examples. So a few years ago, you might have seen something, Google Deep Dream. And this was interesting. It was a first stab at saying, okay, well, we've trained a network to identify all these images, and a lot of them are animal images. What happens if we run it in reverse? So you get some things that look vaguely animal-like, but really you get nightmares. Like it's not going to make anyone think this is a real picture of a dog. But it's an interesting first step in that direction. So that's generative networks. They aren't really good enough to look realistic. But it turns out there's an advance that's happened in the past few years called generative adversarial networks. And this is basically saying having two machine learning networks that train each other. So you have the one network that generates the image, and then you have another network that is trained to determine, is this a computer-generated image or is this a real image? So for example, the discriminator network is the one that says, this looks like what a dog is. A generative network says, here's a picture I made. So the generative network will give a picture to the discriminator, say, I made this picture. The discriminator network will say, oh, this doesn't actually look like a dog, try again. And so they will basically train each other. As the generative network gets better at making pictures that look like real dogs, the discriminator network also gets better at learning what picture is a real picture of a dog versus a computer-generated picture of a dog. So you do get some issues in here in that sometimes one network learns faster than the other network. It's called the vanishing gradient problem. This is not an easy problem to solve, but there's been a lot of interesting work done here recently. So for example, instead of just being able to generate random pictures of dogs, there's been work done to say, okay, we'll take a textual description of something and generate images of it. And we're still not really there in terms of, full quality, believable pictures here. But there's some interesting work being done. So for example, this small brown bird has a pink breast and crown and black primaries and secondaries. And then this algorithm has actually been able to generate pictures that are bird-like, that fit that description. And there's some other interesting examples here with flower descriptions as well. So if you check on Google or you look around, like, this is an area of active research, and there's some really cool examples there. None of them are going to convince people they're real yet, but you can imagine in a couple of years they'll probably cross that threshold of being super realistic. And just to give an example of how far we've come, this is work that was released, I believe, 4 or 5 months ago. Within the last 6 months, the faces on the left are generated by computers using generative adversarial networks a few years ago. The faces on the right are computer-generated images of faces. Those are not real people. NVIDIA has been doing some amazing research into basically creating ultra-realistic, high-resolution photos of faces. So those look like real people. They are not, in fact, real people. You can still see some artifacts, like, for example, around the woman's left ear. But it's amazing how far this has come. Like, at this point, they're still very hyper-tuned, so pictures of faces are easier to generate because we have so many examples of different faces. Pictures of bedrooms is another example that researchers have pulled a lot of pictures of bedrooms from, like, home magazines, and those are less believable. But we're getting to a point where in the near future, it'll be hard to tell if something is a real image or effectively a photoshopped from nothing, which is interesting and kind of scary. So something we'll look out for. Another, so that's interesting, but what's a potential real use case for this? So generative adversarial networks, I showed you how you could go from text to image, but there's also something really cool called pix to pix that allows you to go from image to image. So some of the examples that have been shown with this, if you've ever seen neural style transfer, there's a few apps for iPhone and Android that were popular last year and the year before, that you could take a picture of yourself and applied a fancy filter that made it look like a Monet. So basically what that was, it was taking the input of the picture of yourself and then applying a process that said, okay, well, given a picture of a person, here's what a Monet picture of a similar person might look like. But that can be applied to also other real world scenarios, for example, architecture drawings or handbags or things like that. So there's this really cool tool. You can use it yourself. There's an online demo called Pix to Pix that they took a bunch of pictures of building facades and annotated them with what was in the different parts of the pictures, and then made it where you can actually draw out windows and doors and balconies, and it'll actually generate new nearly photorealistic images of what that building's facade might look like, which is pretty cool. And you can imagine this, having other real-world use cases, for example, beyond just architecture. But there have been some examples where people are designing handbags by basically drawing a sketch of a handbag and then having it actually show what a photorealistic version of that might look like. As far as designers, so you can imagine being able to eventually draw out what you want a website to look like, and maybe being able to eventually output the actual HTML for the site. That's not convolutional, but it's kind of this idea of translating one input to one output, which is definitely an area of active research. So again, here we've taken the initial building, we've added a balcony here, and you can see on the right the balcony is added. Let me go through and just show you the before and after again. Now you'll notice it also changed the color of the building slightly. That is one area where generative adversarial networks still have issues, is they've kind of learned semantically what's important inside of a network or inside of an image, but they still have kind of weird correlations. So apparently the more balconies you have, the more likely your building is to be gray versus a nice sunnier looking brick. And this might be borne out in the data, but it's not actually, doesn't necessarily in the real world require correlation. So that's something where there's still work to be done. But it's still pretty interesting kind of how photorealistic that looks. So generative adversarial networks, as in a book selling solution, maybe not yet, but someday, hopefully, given a title of the book, maybe you could generate a cover for that book. So you got someone, cranking out short stories rather than having a full-on publisher try and create a good cover. Maybe a network could propose good covers for that book. Next, we're going to change gears a little bit. We've talked mainly at this point about input and output. But a recurrent neural network runs over time. So this basically operates on sequences. So whether those sequences are input text or speech or video, anything that operates over time on sequences, you would handle with a recurrent neural network. So for example, you might have seen some examples on Facebook over the past few years of what would I say, or what would Roger say? And basically what they would do is they analyze your text, all your posts over time, and then it generates text that you might say based on the words you use and what sequences you use them in. Actually, the keyboards on iOS and Android do something similar. The text suggestions are based on words that people in general use, but then also they're trained on words that you use. Here you can see some Shakespeare, which if you're not in the literary field, may or may not actually sound like Shakespeare, but it's actually generated by a network that ingested all of Shakespeare's complete works and then output stuff that sounds a lot like Shakespeare. Someday someone's going to actually have a play that's just computer generated, and it'll be interesting to see. On the right, though, you can see some C code that's been written using the same algorithm. This is just a recurrent neural network that's been fed, I think, the entirety of the Linux kernel, and it's actually learned not just the syntax, but it's learned like how to write comments. It's learned structure, and this is pretty exciting. I mean, you can see this code has a lot of structure. It doesn't necessarily make a lot of sense in terms of variables don't necessarily relate to anything in the real world. So it's still kind of babbling. It's not actually doing anything, but the structure is fairly valid, which is pretty interesting. And you can imagine training a network on the entire Linux source code, but then also having having it try and output networks or output code that actually compiles, and having that as a way to train, okay, the code is outputting is good or bad based on whether it compiles. It still probably wouldn't do anything interesting, just like the text on the left doesn't necessarily mean anything useful, but having it appear to be accurate is the first step before figuring out how to actually make it have real meaning. So how does that work? So kind of at a high level, recurrent neural networks have different layers, just similar to a convolutional neural network, but instead of looking at pixels and how they relate to each other, it tries to figure out sequences. So in a sequence of characters, you might have a specific node that learns over time that slashes happen most often after in the case of a URL, a period, another slash, or an M, because the M in .com often is followed by a slash and the colon HTTP. So you can see with the darker blue is where a particular node on this network might get excited and might fire. And then basically the entire output of what comes next is the combination of all of these different nodes and how they relate to each other and what the network thinks is most likely. So individually, they're not necessarily accurate, but again, part of this concept of the neural network, it's got lots of layers. You train it on the simple case, but then eventually it learns kind of these deeper patterns, and it learns kind of how to relate things to each other. Similarly, a recurrent neural network is how you would handle speech recognition and speech synthesis. So in the real world, the way you would do speech recognition is you would take the audio. Hold on a second. There was a question, what does co-ID mean, or is that a typo? Where was that a while back, or did I miss? Lisa, would you mind telling me where that was, the co-ID thing, so I can have some context? Something on screen. So I'm mainly seeing, I'm only seeing my my PowerPoint presentation. Is there something else on the screen that is showing up for you guys? Oh yeah. So again, the code is not actual code. This is just something that was generated by a recurrent neural network. So given examples of lots of C and C++ code, it output this code. It doesn't mean anything. It doesn't actually do anything. This wasn't written by a human though. These are basically, it said, okay, well, this letter after that letter after that letter feels like it could make sense. So again, we're not at the point where it's outputting useful code that's actually doing things, but the fact that you're trying to ascribe meaning to it and you notice that something is out of place kind of really speaks volumes to how good it is overall. Because this was just randomly output by a computer with no real idea of what it was trying to do. It just wanted it to look like the code in the Linux kernel. So again, not quite there yet where everything makes sense, but it's pretty darn close. Hope that that clarified it a little bit. Sorry if I didn't explain that very well. Yeah, actually, there's been some as far as self-documented code. There's been some work done recently correlating code examples in Stack Overflow and GitHub code comments to try and allow you to search for code based on what it does. So I don't have a link in here, but if you search on Google for machine learning code summary or code definitions, there's been some interesting work on basically saying, I want to search for code that sorts things, or I want code that will generate something, and then it basically would be able to understand what code does that based on training of the comments of that code in mass on GitHub, which is pretty exciting. I haven't heard of Source Graph. Is that something similar, Lisa? So it sounds like maybe Source Graph is something along those lines, worth checking out. Cool. Well, anyway, back to back to the presentation here. So recurrent neural networks, again, handle things in order, but it doesn't have to be text to text or character to character. You can correlate things across mediums. So for example, in speech recognition, what you would do is you take the audio from someone saying, this is a test. You run what's called a Fourier transform over it, which is not a machine learning thing. It's just a way to translate the waves of the audio into an image. And once you have that image, which you can see on the bottom, that's the part with the different colors. So that's over time, it's showing at different frequencies, how intense is the sound at those frequencies. You might notice some patterns in there just looking at it with your own eyes. So for example, you'll notice when there's a T sounds, you have, or just letter sounds in general, you have a pretty bright red spots. The S's are more on the high frequencies, and the T's are more on the low frequencies. So as a human, if you look at this enough, you might start to be able to recognize words within these colored patterns. So you basically train a computer to given these input patterns correlated to text, and that's more or less how speech recognition works. It's just recurrent neural networks trained on this kind of data. So recurrent neural network in our ebook example might be able to say, translate this book summary into Spanish. Because again, anything where you have a sequence of input and you want a sequence of output. And the last type of machine learning we're going to talk about is reinforcement learning. Reinforcement learning is different from the other types we talked about. Because the other types we talked about have inputs and they have outputs. It's a process. Training them is a process, and then you have this train network, this train model. You can then run to do inference and run it on new data. But reinforcement learning is more of an idea of having an agent. So if you've heard of Google's AlphaGo, the system that beat the world grandmasters in Go a couple of years back, that was an example of reinforcement learning. So an agent that interacts with either the real world or a virtual world over time, it has to interpret the world, it has to be able to plan for the future, figure out what's important in the future and how its actions are likely to affect that. So it's a much more complicated problem that actually involves solving separate problems in sync. An example of reinforcement learning, often these are trained on video games. There's a lot of interesting competitions going on now in games like a bunch of competitive video games where Google and a few other teams are basically training AI to compete against humans. And they're not there yet to beat humans, but they're getting pretty close. So again, reinforcement learning takes into account what is the state of the world, how is it likely to change based on my different actions, and then determine which action to take. And depending on how that ends up affecting the world, it learns to better predict how its actions affect the world. So reinforcement learning in this case, might be able to envision a scenario of what happens if our ebook company partners with Amazon. What are the potential upsides or downsides if you're able to simulate that? And there actually is some work being done in terms of simulating things like global geopolitics. If you can, try and simulate the different actors at play, the different governments, the different people who care about different things, and you can try and simulate what are the possible actions they might take, what are their possible incentives, and run through different scenarios, basically simulations of different possible outcomes. That's definitely, there's so many unknowns there that it's hard to do that accurately, but there are companies that are attempting to do that to some degree. And you can see that kind of at play in companies that are trying to predict the stock market or things along those lines. So one thing I do want to talk about, you hear so much about all this machine learning, requires big data, a lot of companies collecting data, a lot of privacy invasion, a lot of sense of, okay, well, in order to make a network that can recognize cats, we need lots of pictures of cats. It turns out there's a way around that in some scenarios. So let's say that you are starting a startup and you want to recognize something that you just don't have a lot of input data for. It's possible to actually train a network on an existing data set that is similar but not the same, and then tweak it on your smaller data set. So for example, there's been some really interesting work done on identifying tumors from CT scans. And this is something that doctors generally or technicians are trained to do, and it's not easy even for a human. It's pretty easy to get it wrong. And there's just not enough sample data to train a complete machine learning system to do it from end to end. But it turns out, because it's an image-based problem, if you train a machine learning system on standard image recognition, remember I showed you earlier earlier in the presentation how machine learning might recognize faces and how the lower levels learn to recognize lower level patterns and then how they relate to each other. So if you have a system that's trained to recognize just generic pictures of cats or whatever, the lower levels are actually useful for recognizing other things. So you start with this generically trained network, and then you basically chop off the higher level layers that are trained for cats or faces or whatever, and you start training them on your data set specifically. And even if your data set is small, it still trains surprisingly well. So for example, this work being done to recognize tumors with machine learning is actually as good as or better than trained technicians and doctors in recognizing tumors, because it can see patterns that humans sometimes gloss over, even though the data set that was used for training is very small by machine learning big data standards. So one question that kind of comes up, especially when talking to people in the design world about machine learning, is are the droids coming for our jobs? How much can computers and machine learning actually replace human workers? So I think at this point, machine learning, again, it's narrow AI, it's focused on certain tasks. It can be helpful in your job, but it doesn't necessarily, it doesn't understand context enough to replace most jobs completely. But the helpful aspect is interesting, because here's an example of something someone named Tiff Zhang made just for fun. This isn't a business, this is just a silly little side project. And it generates websites. And they're not perfect, they don't make a ton of sense, but they're close enough to what you might see from some standard Silicon Valley silly startup. You've seen enough different startup websites. This will look about right to you. And it's not perfect, but it's a good first pass. And I think part of how machine learning can really be useful today is to have it be part of the pipeline. Maybe you generate a bunch of first passes of websites, you show that to the client, say, hey, do any of these look okay to you? And then you spend more human effort on actually making, the one that the client likes the direction. You spend more effort on actually, building that out manually. So again, they're not making websites completely yet, but by starting with that and then tweaking it, you might be able to have more creativity, because you can look at more different options, and also just reduce the overall time from idea to completion by having computers help with the parts of the process that they are good at. So in summary, machine learning is task-specific narrow AI, which basically means it's just solving simple math equations, or sometimes less simple, but it's not consciousness. It's not actually intelligence. That's why I kind of prefer the term machine learning over AI, because AI kind of implies that there's some intelligence there. And a lot of this looks intelligent until computers do them. And that now we're like, oh, it's not intelligent. 10 years ago, a computer that could tell a picture contained a cat or not, that was intelligent because it was just so out there for what we expect computers to be able to do. But nowadays, we don't really consider that intelligence. It's just another algorithm that computers have. As far as being able to use machine learning in your own work, you don't need to really understand the math that well. It's good to have a high-level understanding of how the different systems work. You don't want to apply, a convolutional neural network to a problem that's best solved with reinforcement learning. That wouldn't really work. But if you know what types of algorithms to throw at different problems or different situations, then it should be pretty easy to, using a little bit of Google and a little bit of examples out there, find either a pre-made solution or a solution that's close enough that you can tweak it to solve your specific use case. So we're not necessarily, you don't need PhD level machine learning research here. We're kind of at a point where applied machine learning is pretty valuable. The type of algorithm used depends on the problem you're trying to solve. Again, pretty obvious, but machine learning is kind of a broad term of a bunch of very specific algorithms, not one general algorithm. You also might not need big data. Big data definitely helps if you have a very complicated problem space with lots of different facets and you're trying to figure out what's important in there, and or you're, for in examples of generating the C code or the Shakespeare, the more data you have, the more examples you have, the better the output. But it's possible if you're trying to solve you have a use case that's using data that's somewhat similar to a previously solved use case. For example, you're trying to recognize rooftops or you're trying to recognize tumors, then being able to start with an existing trained network that just recognizes images in general and tweaking your use case can let you avoid the need for massive big data. And in a general sense, don't be afraid of computers replacing your jobs, but get creative. Use machine learning to enhance what you do. Be more productive by figuring out parts of your day that can be automated by machine learning, or be more creative by finding parts of your job where machine learning can throw out a bunch of potential solutions. And maybe if most of them are crap, that's okay. But a couple of them might be potentially good seeds of ideas that you hadn't thought of. Again, my name is Roger Pincombe. If you have any additional questions, my email is roger@pincombe.com. We're also going to take a few questions after this. My website is rogerpincombe.com. You can, there's a full video of a previous version I gave of this talk on there. You can reach me on Twitter and GitHub at OKGoDoIt. And I did want to say, when I was putting a picture of myself in this presentation just so you'd have an idea who I am. And in PowerPoint, I pasted the picture and it popped up and it said, hey, how would you describe this to someone who's blind? Let's help accessibility for people who can't actually see this picture. And this is a thing that exists in various tools, software where you can add alt text, but a lot of people don't do it. It's not something, it's a good thing to do, but I think a lot of people just kind of skip it because, targeting blind users is necessarily for someone who has good vision.